Okay, good evening, ladies and gentlemen. It's the wee hours of the morning. I'm making this latest video to get it posted on you. We're going to talk about some limit stuff. I'm going to continue using the same Smart Notebook file that I had before on the first limit review. So this is going to be called Limit Review 2 or the LHopital's video. But if I go back here, the first part of day one limit review talked about these graphical limits. And this is on that first video. Okay, this is going to be an important topic. This is certainly a topic that you're going to need to understand, graphical limits. And then I think here I did another graphical limit, but here I added some vertical asymptotes, very important. I may talk about some horizontal asymptotes later on in this video, but you need to understand vertical asymptotes. And then I ended that first video with just some basic analytical limits, how to do limits analytically. And that's kind of what we're going to follow up with, but I'm going to look at some of these limit laws down here, and I'm going to look at one specifically. This one here I'm going to look specifically at because we're going to use this for LHopital's rule. So this is going to be super important. These two laws are not, the law A and law B are pretty straightforward. I think, yes, indeed, this guy right here, this was an application in which you could direct substitution. The first thing you do with analytical limits, you just do the direct substitution. If you get a real number, bam, you're dumb. You're not dumb, you're done. And then this guy here, this is an important law too. This is just the constant multiplier. If I have k times a function, I can pull the k out and then do the limit. That's basically what I did right here. I just pulled the 7 out, this constant multiplier, and then just took the sine of pi over 6. So these two guys right here are pretty straightforward. I'm going to concentrate on this right here in this video because we're going to use this particular law for LHopital's rule. Okay, so here we go. We're going to look at some examples here. Okay, these particular examples are pretty easy. I'll let you, I can do them real quick if you like. The limit as x goes to 3 of f plus g. It's going to be this guy right here. It's simply going to be 2 plus negative 4, which is negative 2. Easy enough. This is 5 times. This is going to be negative 20. Easy enough. And this, as the limit is f of x is going to go, this is simply going to be, this one here is undefined because I get this 2 divided by 0. So that one's undefined. What I want to look at, and I want to concentrate on these quotients, the limit of a quotient. This is a limit of a quotient too, but here's the way you're going to want to write the limit of a quotient so that we can use LHopital's rule correctly. And so we want to get used to doing this. And so here's how we're going to do this. We're going to write this as a limit as x goes to 0 of the sine of 5x. And we're going to put a big long division bar here. And we're going to use this, for what we're doing is employing this property right here. We're employing this property, this dude right here. This is what we're doing. We're going to use this big division bar. Okay. And I'm going to write the same thing. I'm going to write the limit out for the denominator. The limit is x goes to 0 of 2x plus 5. And now before I evaluate that, I'm actually going to, now I have created, this division bar is going to do two things for us. It's going to allow us to see the quotient of these two limits, but we're going to look at those quotients as separate human beings. Well, not as human beings, as separate entities. This is exactly what we're going to do, look at them as separate entities. And so I'm going to evaluate this top limit right here. And this top limit is going to, x goes to 0, 5 times 0 is 0. The sine of 0 is 0. And if I put 0 into this, 2 times 0 is 0, plus 5 is equal to 5. Now and only now, and I could have done that up there at C, but now and only now I can say, since 0 divided by 5 is 0. that guy a 0. Okay. Let me get this guy out of my way, see if I can take this guy and move him. I can. Okay, so now I'm going to do this guy right here the same way. Okay, I'm going to look at the limit at the top. The limit is x goes to 25, and the square root of x minus 5, and I'm going to put a big division bar here. It kind of separates the two things. It separates the two limits. Look at this limit at the bottom. X goes to 25 of x minus 25. Okay, and I'm going to evaluate each of those limits separately. Okay, just like I did up here. Well, what does this top thing goes? Well, if x goes to 25, square root of 25 is 5. 5 minus 5 is equal to 0. As x goes to 25 of x minus 25, that goes to 0. Keep in mind, we are not going to, this is a no-no, we are not going to write this way. We're going to write it as two separate limits. Limit of the numerator and the limit of the denominator. And that division bar is just going to separate things for us. Now we need to know what happens if the limit of the numerator is 0 and the limit of the denominator is 0. And we're not going to say that that equals 0 over 0. That's the no-no. Now here's where I'm going to employ LHopital's rule. We talked about LHopital's rule. I'm trying to make it simpler for you, an easier way to determine that. And so here's my condition. If the limit is x goes to a of f of x is equal to x divided by g of x, and I'm going to use that quotient property that I talked about, and I'm going to look at this big giant division bar here. I'm going to look at the limit at the top. The limit is x goes to a of f of x, and I'm going to say if the top goes to 0 and as a separate bottom is a separate limit, if the limit of the bottom goes to 0, then here's my conclusion. Then this limit, the limit is x goes to a of f of x divided by g of x is equal to the limit is x goes to a of the derivative of f divided by the derivative of g. But I have to, first and foremost, I have to have these two separate limits here. I have to show them as two separate limits. And this could very well be a free response this year, and it will be a question that we're going to be asked on the quiz Friday. Okay. So how am I going to apply this on this problem right here? Well, the first thing I notice is that you dig and dog right. I have the top limit that goes to 0, the numerator, and I have the bottom limit that goes to 0, and they are indeed separated by a division bar, and I do not have it written as 0 over 0. So now I'm going to come down, I'm going to implore LHopital's rule, and I'm going to say, hey, kids, x goes to 25 of this guy right here, square root of x minus 25 over x minus 25 is equal to the limit, I'm going to implore LHopital's rule, x goes to 25, and what's the derivative of the top? It's the derivative of that guy right there, square root of x minus 25. Let's see, what is that? Oh, yeah, it is. 1 over 2 square root of x. The derivative of 25 is 0. And now what's the derivative of the bottom? The derivative of the bottom, what is the derivative of x minus 21? So this limit, because of this, because of that, because I have these two separate entities, I can implore LHopital's rule, and I can write this limit as that, and now I'm going to evaluate that limit. 1 over 2 square root of x divided by 1 is just 1 over 2 square root of x. And now I'm going to do direct substitution. Square root of 25 is 5, and that's simply going to equal 1/10. Okay, we're going to do another LHopital's rule. I'm only into 9 minutes into the video. So I just did an example of the LHopital's rule here. I'm going to come down here and do another example here of the LHopital's rule. And I'm going to look at this guy right here. And I'm going to use the quotient property. Take this guy right here, move him over here right now. I'm going to use the quotient property. I'm going to say, oh, that's equal to big division bar, big old division bar. The limit as x goes to 0. And I hope that you don't, I'm going to have to take off if you don't write this step. If you don't, because this is the most important step right here. You're going to need to write that step. That limit is x goes to 0, and you notice I'm just going to evaluate it as a separate limit because it is a separate limit in its own. As x goes to 0, 5 times 0 is 0. Sine of 0 is 0. And now I'm going to look at the limit of the denominator as x goes to 0. And all I'm doing is using that quotient property. When does x goes to 0? Where does 3x go? 0, 0. So now, since I have the limit of the numerator going to 0, as I do, and the limit of the denominator goes to 0, as I do, and since I have them written as two separate entities, I can go here. I can take this guy, x goes to 0, of sine of 5x, or 3x, and that's going to be the limit as x goes to 0 of the derivative. So what is the derivative of this guy right here? Well, the derivative of sine, hello, neighbor, is cosine of 5x, right? Oh, no, keep in mind I have to differentiate this. I have to multiply this by the derivative of the inside, and the derivative of 5x, folks, is 5. So the derivative of sine of 5x is 5 cosine 5x. And the bottom derivative is going to be pretty easy. Oh, hello, neighbor. The derivative of 3x is just 3. Therefore, this limit right here is going to be the limit of 5 times the cosine of 5x over 3. And now I can do direct substitution, because I know I'm not going to have a 0 on the bottom or a 0 on, or 0. It doesn't matter if I have a 0 on the top. I'm not going to have the limit at the top is going to be 0, and the limit at the bottom both will not be 0. So I'm going to do direct substitution. If I put 0 in, cosine 5 times 0 is 0. Cosine of 0 is 1. So that's just going to be 5. And the limit is x goes 0, 3. Where does 3 go as x goes 0? 3. So therefore this limit is 5. And I will tell you, this problem, if this problem were worth 2 points, if you did not have this, you would get 0 out of 2. If you have this, you're going to get 1. But then you need to write, you're going to need to employ LHopital's rule, and this is the application of the conclusion of LHopital's rule, where I take the derivative of the top and the derivative of the bottom, and I evaluate that. Okay, so we're at 13 minutes here. I'm going to do one more quick topic. Keep in mind this particular video was mostly about LHopital's rule video. LHopital's rule video. Well, what? Okay. The last thing I'm going to do with this is, because there are a couple reviews. These are pretty easy, so I guess it's worth talking about. We're just going to take, and this is going to be, this is for the non-BC students. This is just for the AB students. And I'm taking the limit, just to discuss real briefly how to take the limit as x goes to infinity. There's going to be some IXLs on that. You can simply use the Cribbillion method. If you can't get these right, the IXL goes through a very difficult, convoluted process. But you don't have to worry, you don't have to use that. All you need to do is use the Cribbillion method from last year. And what does that Cribbillion method tell me? Well, if I'm going to look at the top at Cribbillion, I'm going to evaluate the top at Cribbillion, and this is going to be 3 Cribbillion cubed minus 7 times Cribbillion plus 4. The Cribbillion method always works when you have a quotient of 2 polynomials. Well, 3 quadrillion cubed is so big, all of this stuff here is really insignificant. So all I need to do is look at the leading coefficient of this, which is 3x cubed, in like a manner. Quadrillion cubed plus 18 quadrillion, this really doesn't matter. It's what we call insignificant. So I'm only going to look at the leading terms. And where 3x cubed divided by x cubed, when x is a positive number, is simply 3. There's going to be a couple limits as x goes to infinity on the IXLs. It should be an easy topic to do. Don't make it more difficult. So this video mostly was about this LHopital's rule, and that's going to be everybody's going to need to know how to do that A, B, and B, C. So I'm going to close this video. I'm going to process this and post this, and I'll talk soon.